To begin discussing error analysis, we really need to understand something about measurement theory. And so I'm going to start us off with a hypothetical set of data, and I'm going to lay down this data set on what is essentially a histogram. So on the y-axis, we're going to have what I'll call the count. This is the count of each type of measurement. And then along the x-axis, we're going to have some measurement scale. Let's imagine that we're measuring the pH of a solution. Maybe it's a sample of water pulled from the environment. And we're doing this many times so that we get slightly different values for each measurement, and we can plot them in a histogram by plotting each pH we measure and the number of times we measure it. So if we did this many times, we would get a distribution that looks something like this. The measurements would increase in frequency to a maximally likely or mean value, and then would start to decrease from there. And we see that we would have some outlying values on the outskirts, but most of the values would be centered near the mean, which shows up right at the center of this curve. This distribution, which shows up again and again in science, has a special name. It's called the normal or Gaussian distribution. And the normal distribution shows us that measurements are spread, that if we execute the same measurement multiple times, we should expect a spread of values as we perform the measurements. The relation of this to errors is twofold. So on the one hand, we see that there's some error in the sense that if the mean is really the true value, the measurements that we execute individually are not necessarily equal to that true value, but are distributed about the center. So the spread that we see, that I've represented with this arrow here, comes from a particular type of errors. The other type of issue that comes in is if the true value is not exactly identical to the mean, say that the true value shows up where I'm drawing this white line here, then there's a distance between the mean value and the true value, and that distance is related to another type of error that we'll discuss shortly. So, as you may have surmised already, this distance between the true value and the measured value is an issue of accuracy. The data appears to be inaccurate, shifted from the true value at its mean. And to represent that, we can calculate the percent error by taking the difference between the mean measured value, which is the pink dot in the center, and the true value, which we know through some external means. Maybe we know what the pH of this environmental sample should be. The spread in the data, which is represented by this arrow within, showing the fact that the normal distribution is not a single sharp line, but a wide distribution of values, that's an issue of precision. The data are imprecise, meaning that they're spread out with respect to the mean. Not all measurements are exactly on the mean, and that's fine, that's okay. That's the nature of science and human exploration. To quantify the precision, we can talk about the standard deviation of this set of measurements, which is essentially a measure of this internal deviation from the central mean value. For a distribution that is a perfectly sharp spike, something like this, the standard deviation is at or near 0. For a wider distribution, like the one we see at the bottom here, the standard deviation is greater than 0 and indicates some imprecision. Now you may be asking yourself at this point, what do accuracy and precision have to do with errors? And the key insight here is that two types of errors impact each of these measures of data quality. So accuracy, as we'll see in the next video, is impacted by systematic errors. We'll talk about what we mean by systematic in the next video, but take my word for it for now that systematic errors impact accuracy. Precision is impacted by random errors. Random errors don't affect accuracy, systematic errors don't affect precision, but systematic errors do affect accuracy, random errors precision.